We will now discuss some operators that arise in multivariable calculus. These are some standard operators that will be used in the subsequent lectures. So first of all, we'll look at the vector operator that does partial differentiation. We need to keep in mind what the operator operates on, i.e. scalar or vector, and what the end product is, scalar or vector. So the first of these is the del operator. And we define the del operator as the vector operator of partial differentiation. So if you're dealing with 2, 3, or a number of variables, then the del operator, for example, would be in 3 variables: d by dx, d by dy, d by dz. The del operator operates on a scalar function giving us a vector, so that if the function phi is a function of in this case 3 variables x, y, z, then the del operator on the function phi is then defined as this vector operating on phi, which gives rise to the partial derivative of phi with respect to x, the partial derivative of phi with respect to y, the partial derivative of phi with respect to z. You will notice that in this case the del phi is exactly equal to the grad of phi, the grad being the operator we defined earlier on. So that a simple example would be an example we've looked at before, that if phi is equal to, say, x squared minus yz, then the del of phi would very simply be the derivative of phi with respect to x, the derivative of phi with respect to y partially, and the derivative of phi with respect to z partially. So that's a straightforward example. Right. Following from that, we will define the div operator. So the second operator is the divergence operator. Or let me just say that is the short for divergence. And the divergence operator operates on a vector to give us a scalar. So that if the vector v is a vector, so suppose the vector v in this context is a vector of 3 coordinates, i.e. each of the components v1, v2, v3 may depend on x, y, and z. We define the divergence of the vector v to be equal to the sum of the following partial derivatives. So in this case, you've got the first component v1 differentiated with respect to x, the second component differentiated partially with respect to y, the third component differentiated partially with respect to z, and then we add these 3 things. In the case, of course, of 2 variables, it will be v1, v2, etc., etc. If we look at this closely, we can rewrite the divergence in terms of the del operator. It is very clear that this is the dot product of the operator partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, dotted with v1, v2, etc. So that this can be written as this first operator is the del operator dotted with the vector v. So you may want to remember this as the del dot v. So keep in mind that the del operator operates on a scalar to give you a vector. The divergence operator operates on a vector to give you a scalar. So let's just go back slightly and highlight these differences. So in this case, for example, we have that that is the del phi equals the grad of phi, and the divergence of a vector field. So this is, of course, if we're writing this is the divergence of the vector field V, and if we highlight that, that would be this operator defined as the del dot the vector field V. So divergence operates on a vector to give you a scalar. Okay, so as a consequence of these operators, we may now define further operators. Okay, and the next operator is the curl operator. The curl operator is the operator that operates on a vector to give you another vector. So now we define the curl operator. And as a definition, we say the curl of a vector V. So there already it is clear that the curl operates on a vector field, on a vector, and that ends up giving us a vector. So this is defined as the del operator we mentioned earlier above, cross product with the vector field V. So that we can regard as the definition of the curl. Again, I emphasize, note that the curl of a vector gives you a vector. Okay, so let's spell this out. So i.e., if you write this out, the curl of the vector field V is determined by definition. The curl, the cross product of two things is I, J, K. The del operator is the partial derivative with respect to x. I'll write it as partial derivative with respect to y, partial derivative with respect to z, and the third row is the vector field V, which is V1, V2, V3. And this, of course, we can write out as a vector. The first component of this vector will be the cross product, the determinant of the 2 by 2 matrix that I'm going to indicate here. So the first component is the determinant of this 2 by 2 matrix, which is the partial derivative of V3 with respect to y. So this is the derivative of V3 with respect to y minus the partial derivative of V2 with respect to z, comma, and then we take the determinant of the following 2 by 2 matrix multiplied by a minus sign. Now if you look at this 2 by 2 matrix, right, we take the determinant of this 2 by 2 matrix, but remember here that there's a sign change being the middle component. So here it's the derivative of V1 with respect to z So this is the derivative of V1 with respect to Z minus the derivative of V3 with respect to X. And the last component is the determinant of this 2 by 2 matrix that I'm putting in that color there. So here it's the derivative of V2 with respect to X. So this is the derivative of V2 with respect to X minus the derivative of V1 with respect to Y. Let's close that back. that is the curl of a vector field V in 3 components spelled out. So keep in mind that the curl of a vector field may only be defined as it stands on a 3-component vector field or vector. If, however, the vector field or the vector V is of 2 components, we let the third component equal 0 and then define the vector, the curl accordingly. So note, if the vector field V is of 2 components, then we redefine for the curl purposes the vector field V to be V1, V2, and 0, so that the curl of the vector field V, the curl of the vector field V, which of course is always del cross the vector field V, will very simply be, it will be clear from above that the first 2 components will be equal to 0, and we left only with the third component. So this is always the case 0, 0, and what we end up with in the third component is what we have above, which is the derivative of V2 with respect to x minus the derivative of V1 with respect to y. So we had the del, we had the div, and we have the curl. Unlike the first 2, the curl operates on a vector to give you a vector. So let's do 1 or 2 examples before I get to the final operator. So example, suppose the vector field V is a vector field containing 3 components given by x, y, y, z, zx. So suppose the vector field V is x, y, y, z, comma, zx. Just to give you a simple example, then it is clear, first of all, that the div of this vector field, which is going to be a scalar, you differentiate the first component with respect to x partially, the second component with respect to y partially, the third component with respect to z partially. So that's straightforward. If you're doing the curl of the vector field V, then that is going to be, of course, a del cross V, which is in terms of cross products given in the following way. We have partial with respect to x, partial with respect to y, partial with respect to z, and then we have x, y, y, z, zx. And if we are to spell that out, you're differentiating zx with respect to y minus differentiate yz with respect to z. Then remember here the order changes. For the second component, you're differentiating xy with respect to z, and then zx with respect to x. That gives you z. Note the order for the second component. And then in the third case, third component is the derivative of yz with respect to x minus the derivative of xy partially with respect to y. So that gives you very simply the vector minus y minus z minus x. It's a rather simple example, but it makes the point quite clearly. You can try some examples from your tutorial books. They of course are not as straightforward, but let me do one simple example involving two components and finding the curl of that. So if your vector field V is defined as e to the x times y minus e to the y times x, then for the curl we said that we extend this vector field V to a third component involving 0. So then the curl of this vector field V will always have the first two components equal to 0, and to determine the third component we just go back and we get exactly the same component. Here it is. If you look at that, it's basically determining that component. You differentiate V2 with respect to x minus differentiating V1 with respect to y. So it's V2 with respect to x. That means if you differentiate V2 with respect to x, you get e to the y times x minus differentiating V1 with respect to y. If you differentiate V1 with respect to y, it's 1 times e to the x. Done. Okay, there will be one last operator that is a consequence of this del operator. Okay, so recall that we said that the del operator is a vector operator containing the partial derivatives with respect to x, with respect to y, and with respect to z. If we define dels, then we may define an operator del squared. Then del squared is defined as, so that is del squared, we define that as del dot product with del. And if you do that, what do you get? You get d dx, very straightforward, d dy, d dz, dotted with itself, d dx, etc. And if you work that out, so it's d dx on d dx, you get d2 by dx squared, d dy on d dy, you get d2 by dy squared, and similarly d2 by dz squared. Remember, this is an operator, and these three things are added. So there's del squared. So the del squared operator is an operator that would operate on a scalar function to give you a scalar. And of course, this can be defined very easily. It can be adapted to two components. In two components, you'll just get d2 by dx squared plus d2 by dy squared. This operator is also called the Laplacian. So the del squared operator is sometimes referred to as the Laplacian, named after Laplace, of course. So as an example, let's do it on a two-dimensional function, i.e. based on two independent variables. If phi is e to the x multiplied by the cosine of y, then the Laplacian on phi, then del squared on phi is very simply, well, you differentiate phi with respect to x twice, plus you differentiate phi with respect to y twice. And if you did all the calculations, remember these are partial derivatives, and in this particular example you end up with 0. And there's a significance in that. It need not be 0, of course, But if it does turn out to be 0, then so be it. Okay, now just something about the 0. Some further definitions. If the Laplacian on any function, and I'm going to use a different notation here, if the Laplacian on any function psi is equal to 0, we say that first of all, the function psi satisfies the Laplace's equation, and we say psi is a harmonic function. Then we say, it's a definition, we say psi, whether it's in 2 variables or 3 variables, is a harmonic function and the differential equation, it's a partial differential equation, the differential equation d2 by d2 of phi by dx squared plus d2 of phi by dy squared for any number of variables, of course, d2 phi by dz squared, etc., equal to 0. This is a partial differential equation. This differential equation is called Laplace's equation. Is called the Laplace's equation. So it's clear that any solution of Laplace's equation, any solution of this equation, is called a harmonic function. That's a nice color there. Thus, let me just make that as a final statement. Thus, a solution of Laplace's equation, a solution of Laplace's equation is a harmonic function. We will discuss harmonic functions very soon again in some other context. Thank you.